Now that we've covered the basics of partial derivatives, let's now look into uh, partial derivatives as the two of the most basic functions of derivatives. And the first two would be a slope. So the geometric interpretations of the partial derivative of a function of two variables are similar to those of the functions to a function of one variable. The graph of the function f having two variables has a surface having the equation z is equal to f of xy. So something like this. If y is held constant, say y is equal to y sub 0, then c is equal to f of x comma y sub 0 is an equation of the trace of this surface in the plane of y is equal to y sub 0. So for example, you have this here, this is the plane. So once the graph of the function z intersects if y is held constant, then you have that specific trace there. And the curve can be represented by the two equations, y is equal to y sub 0 and z is equal to f xy, because that curve is the intersection of the two surfaces. Therefore, the first partial derivative is the slope of the tangent line to the curve. So the partial derivative here is the slope of this line, given by the two equations in the previous bullet, at the point p sub 0 containing the ordered triple x sub 0, y sub 0, and c sub 0. So you can also do that in terms of x. If x is held constant, therefore you're going to have this plane here at x comma x sub 0. So the partial derivative is the slope of this line here, wherein that is a specific point on the curve of z, of the function z, and of this plane. So informally, the values of the partial derivative of the point p denotes the slope of the surface in the x direction and in the y direction, respectively. So let's have example problems for those. So first, in number 1, we're asked to find the slope in the x and y directions of the surface given by f of x is equal to this function at the point 1, 1/2, 1, and 2. So let's first look for that. Let's first look in the x direction. So we have number 1, f of xy is equal to negative x squared over 2 minus y squared plus 25 over 8. So if you want to find the slope in the x direction of this curve, that means we're looking for the partial derivative in terms of x at the specific point. So let's first look for the partial derivative in terms of x. So therefore, this will just find the derivative of this as is. That becomes negative 2x over 2. This, since this is y, this is considered as a constant, so as is. And then, this is actually a constant, so not as is. These two are constants, so the derivative of that would be 0. Simplifying this, therefore, we get the partial derivative of the function in terms of x as negative x. Therefore, the partial derivative of the function at the point 1/2, 1, and 2, which by the way, I'm not going to write 2 because remember, the ordered triple is x, y, z. In the function, you only need x and y, that's why we only have this. So the partial derivative in terms of x would be the negative of 1/2, which is what? Negative 1/2. Therefore, the slope of the curve at the point 1/2, 1, 2 in the x direction is negative 1/2. So if we're going to do the same in the y direction, we're going to need to find the partial derivative in terms of y. Now, that makes this a constant, so the derivative of that is 0. Finding the derivative of this in terms of y, that becomes negative 2y. And since 25 over 8 is an actual constant, the derivative of that is 0. Therefore, if you want to find the slope at the point 1/2, 1, 2, we do the same. But this time, since it's y here, that becomes negative 2 times 1, not 1/2. The x here is 1/2, that's what we replace here. But here it's y, so it's 1 that we replace, and this becomes negative 2. Therefore, the slope of the function in the y direction becomes negative 2. There we go. So, here. Now let's go to number 2. Find the slope of the tangent line to the curve of the intersection of the surface z is equal to this with plane y equals to at the point 2, 2 square root of 3. Going back, if we have the plane here, so if the plane is at y 0, 0, this is the one that remains constant. Hence, the partial derivative that we have to look for is in terms of x. That would mean that if you want to find the slope of the surface with the plane at y equals something, so with plane y equals something, this is your indication that what you're looking for is z sub x or z sub 1. The first part, the partial derivative in terms of x. So to do that, you will just do it here below first. So in number 2, c is equal to 1 half times the, I'm going to write it in terms of a rational exponent so that we can easily find its derivative. 1 half times 24 minus x squared minus 2y squared raised to 1. So if we want to find the derivative of this in terms of x, that would be z sub x would then equal to 1 half multiplied to the derivative of this function. That's 1 half times 24 minus x squared minus 2y squared raised to negative 1 half times the derivative of the ones inside in terms of x. 24 is a constant, so that's 0. There's no x term here, this is also a constant. 0, so that becomes negative 2x. Go. So, if we are to simplify stuff, we're going to cancel this one here because that cancels out. And then this has to go to the denominator because of the negative exponent. Therefore, z sub x will then equal to, I have a negative x on top, over 2 times 24 minus x squared minus 2y squared raised to 1 half. Now, if we want to find the slope of this at the point 2, 2 square root of 3, therefore this becomes negative 2, that's negative x. Negative 2 over 2 times the square root of 24 minus 2 squared minus 2 times 2 squared. So I'm going to have this actually simplifies, so this gets cancelled out. So I'm going to have negative 1 over the square root of 24 minus 4 minus 8. So there. So therefore, I'm going to have 2 square root of 3. I'm going to put 3. Yeah, so this becomes negative 1 over square root of 12, which is actually 1 over 2 square root of 3. So rationalizing, I'm going to have this one negative 3 square root of negative square root of 3 over 6. So therefore, the slope at the x direction with the plane y equals 2 is negative square root of 3 over 6. Go. So pause the video and try to see if you'll be able to find answer question number 3. Alright, so in question number 3, we're asked to find the slope on the surface given by f of xy is equal to 1 minus 1 minus x minus 1 squared minus y minus 2 squared at the point 1, 2, 1 in the xy directions. So both directions. So first, let's find the partial derivative in terms of x. This is constant, so this is what I only need to find the derivative of. Therefore, this becomes negative 2 times x minus 1 times 1. So I don't need to write it anymore. Sorry, I forgot. times f of x times xy. So therefore, if we want to find the slope at the point 1, 2, 1, this becomes negative 2 times 1 minus 1, which ends up with the slope of 0. Therefore, the slope of the curve at the point 1, 2, 1 is actually 0. On the other hand, for the partial derivative in terms of y, both of these would remain constant, so I'm now going to have y becomes negative 2 times y minus 2. So if we want to find the slope at the point 1, 2, 1, this becomes negative 2 times 2 minus 2, which also ends up at 0. So the slope in both x and y directions of the graph of the function f of xy at the point 1, 2, 1 would be 0. Now, apart from being a slope of the graph at a certain point, because a derivative is a measure of rate of change, a partial derivative can be so interpreted, a rate of change. So if f is a function of two variables x and y, the partial derivative of f with respect to x at the point p sub 0 with coordinates x sub 0, y sub 0 gives the instantaneous rate of change at p sub 0 of f of x, y. Let's have a specific example. In number 1, according to the ideal gas law, for a confined gas, if P atmosphere is the pressure, B liters is the volume, and T degrees is the absolute temperature on the Kelvin scale, we have the formula PV is equal to KT, where K is the constant of proportionality. Suppose that the volume of a gas in a certain container is 12 liters, and the temperature is 290 degrees Kelvin, with K is equal to 0.6. The first thing that we're asked to find the instantaneous rate of change of P per unit change in T if P remains fixed at 12 liters. So let's write that down here. So for 1A, we are told that for ideal gas law, that's PV, ideal gas. The ideal gas law, that's PV is equal to KT. In the specific, we are given that the relationship for a certain gas in a container has a volume of 12 liters, a temperature of 290 degrees Kelvin, and with the constant of proportionality of 0.6. The first thing that we ask here is to find the instantaneous rate of change of P in terms of T, which would mean we need to write this somehow as P is equal to something T, with V remains fixed at 12. Now, since V remains fixed at 12, that means I can already write here in the equation that's P times 12 over is equal to 0.6 T. So therefore, sorry, let's not do that first. That's wrong. Again, the first thing that we need to do is to find the expression for the partial derivative. So we need to write this equation, P is equal to something T. So with that in mind, we're going to have PV is equal to KT. We divide both sides first by P. So the P is equal to KT over P. This is now when we can actually place our values, although what we did a while ago is partially correct. We're going to have now P. Actually, we need to place 0.6 on it, so we have 0.6 T over V. Yeah. So with that, if we're now to find the partial derivative of P in terms of T, this becomes 0.6 over V only. Why? Since V remains fixed, that this means that P is a constant. So 0.6 over v is a constant. What we need to derive is only t. And the derivative of that is, well, 1. That's why we have this. Therefore, the instantaneous rate of change with v equals 12 becomes 0.6 over 12. And you end up with, that becomes 6 over 120, or that becomes 1 over 20. 1 over 20. I think that's the simplest word. Therefore, the instantaneous rate of change of p in terms of p would be 1 out of 20 atmospheres per change in degree Kelvin. Here, so we change 1 atmosphere per 20 degrees change in degree Kelvin. That's the instantaneous rate of change of p if volume remains fixed at 12. So pause the video and then try to answer letter B here. Alright, now let's now have letter B. Again, we still have P. V is equal to 0.6T. That's the original equation. And then we're now looking this time for the instantaneous rate of change in V per unit change in P, which is the partial derivative of V in terms of P. Therefore, if we are to rewrite this equation as P is equal to something V, we do the same, we divide both sides by V. Therefore, P is equal to 0.6 T over V. So there you go. Wait a moment. I think we need to change because it's V over P. So the partial derivative of V. So it's not supposed to be P. V is equal to 0.6. It's V is equal to something P because it's the partial derivative of V. So V is the function, so to speak. So it's supposed to be V is equal to something P. So we have to divide by P so that it becomes V is equal to 0.6T over P. So V is equal to something of P. Yeah, that's much better. Now, if we are to find the derivative in terms of P, then this is the one that becomes constant. Therefore, the partial derivative of V in terms of P will then be equal to 0.6T times the derivative of 6T times the derivative of 1 over P. That's actually what this is when you separate that, which is actually negative 1 over P squared. So combining this, we're going to have negative 0.6T over P squared. And we're asked to find instantaneous rate of change of V if T remains fixed at 290. So therefore, we're going to have negative 0.6 times 290. Now, what about P? We need a value of P here. But all we know is that we have a volume of 12 liters. We only have a volume of 12 liters, a temperature of this, and a constant of this. But with that, you can actually compute for the pressure once all the other variables are given. So let's separate that here. So the pressure now becomes so the pressure times the volume of 12 liters is equal to 0.6 times the temperature of 290 degrees Kelvin. So we divide both sides by 12 liters, and then this would then become 14.5. Don't you worry, in the given assessment, we do not use that. So with that in mind, that's what we replace here. So this becomes over 14.5 squared. This actually ends up as negative 24 over 29. Therefore, the instantaneous rate of change of V in terms of P is negative 24 over 29 liters per change in atmosphere. So there you go. So those are examples of the application of the partial derivative as a slope and as a rate of change. The others that are not answered may serve as your own personal exercise.